Hello everyone, welcome back. So this time we're going to be going over another example, and we have a fairly similar situation to last time, except for this time we know the velocity is a function of time rather than the velocity is a function of the path. Also, the radius of curvature is given to us. So what does it want us to find? Well, let's find the magnitude of the boat's velocity and acceleration at the time when t is equal to 10 seconds. How are you going to do this? Well, you've got an equation, plug a number into it. That'll give you your velocity. Then you're going to have to do some derivatives to calculate the normal and tangential components of acceleration. So, I'm going to give you a little bit of time to work on this. It's not too hard. I think it's probably easier than the last problem. And then we're going to come back and see if you did it right. So, 3, 2, 1. Okay, now, hopefully, you paused and you tried to do the example. If you're trying to do it in 3 seconds, props to you, but you don't need to be that fast. Try to take some more time to do your work. I'm sure there'll be very few times where you need a time cruncher that much. And oh my goodness, Lord help you if you are in this situation. So how do we do this? Well, the velocity vector is very simple. We just plug 10 into the velocity equation, because our velocity is only going to have a tangential component, and simply the magnitude times that tangential direction. So we plug 10 seconds into our equation. It comes to be 6.25 meters per second. Now, as I said before, velocity is simpler in the normal tangential coordinate system. Acceleration, not always so much. But it's not that terrible either. Because for one, this is a function of time, which makes any time derivative very simple. So we write out our acceleration. We have two components. We write what those components stand for. Well, we already know the velocity, we already know the radius of curvature, so that one's taken care of. And if we just take a time derivative, we can figure out what v dot is very simply. So, take a simple time derivative, we get the derivative of 0.0625 t squared is going to be 0.125 t. We plug 10 into that, and we get that our tangential component is 1.25 meters per second squared. Now, how about our normal component? Well, that's v squared over rho. We plug in our velocity that we calculated earlier. We plug in our known radius of curvature, and we get a much smaller value, 0.9766 meters per second squared. For take magnitude, we simply put them into our equation, where we square each component, add them together, and then take the square root. Okay, so this time it was actually much more simple. If you see equations with time in it, it's usually going to be a pretty easy problem. It's when they have equations in terms of velocity or equations in terms of the path that things get a little bit more hazy, and you're going to have to use those chain rules. So remember this. Remember that these problems aren't that bad. Just write out your equations, make sure you follow the steps, and you should do well. Thanks for listening, and I'll see you all next time. Bye-bye.